So, in the last lecture, if you recall, we had talked about the concept of Karnaugh map method of minimizing a function, and through examples we showed how we can handle or minimize 3 variable functions. So, in this lecture we shall be extending our discussion to handle 4 variable functions. So, we shall be extending our discussion to 4 variables. Now, recall we mentioned that it is not so easy to extend Karnaugh map concept to larger number of variables. Of course, in books you will see that the authors have said that you can do it up to 6, but up to 4 is easy, 5 becomes difficult, 6 becomes quite difficult, beyond 6 is impossible. So, whatever examples I show here will be only up to 4. Okay. So, if we have 4 variables, then how many min terms are possible? 2 to the power 4 equal to 16. So, first thing is that you need to have 16 cells and they will be organized in a 4 by 4 cell array. So, there will be 4 rows and 4 columns, 4 rows and 4 columns. The basic concept of labeling remains the same. You will see that the way you label the rows and columns, it will always be ensured that the neighboring cells will always be differing in a single variable. This will, and also there will be a neighborhood relationship between the right and left and also top and bottom. Top bottom and left right adjacency will also be provided or ensured. Not only that, you will see that the 4 corner cells will be considered adjacent to each other. Why? We shall see just a little later. Let us consider a 4 variable Karnaugh map like this. This is just an extension of a 3 variable map, where we consider a function with 4 variables, let us say a, b, c, d, where in this diagram I am showing a, b along the rows and c, d along the columns. And just like a 3 variable function, the way we label the columns in the gray code order 0 0 0 1 1 1 1 0, here we are doing the same thing for both rows and columns 0 0 0 1 1 1 1 0. Why? You consider any 2 cells, let us say these 2 cells. The first cell corresponds to 0 1 0 1 0 1 0 1. The second cell corresponds to 0 1 1 1 0 1 1 1. You check, they differ in a single variable, this last position, sorry, second last position 1 0 1, it differs in the second last position, right. Now, you take any pair of cells vertically, take this and this, the upper cell corresponds to 0 1 1 0, lower cell corresponds to 1 1 1 0. You see, these are also adjacent, only the first variable is different, the other 3 are the same, right. The same thing you can extend to a cube of size 4. Let us consider these 4. These 4 corresponds to, I am just writing down the binary 0 1 0 1, then 0 1 1 1, then 1 1 0 1 and 1 1 1 1. So, you see here the second and the fourth variables are the same 1, this is also 1, but the first and the third variables, which is a or c, they are changing. So, if you form a cube out of these 4, this will be corresponding to b and d, minimized form will be only b, d, a and c will, they will be cancelled out. Similar is the case if you take a cube vertically like this, they will correspond to 0 0 1 0, 0 1 1 0, 1 1 1 0, 1 0 1 0. So, again this 1 0 is common, the first two are changing, they will cancel out. So, C and D will remain, it will be C D bar 1 0, right. Now, I talked about the 4 corner cells, right. Suppose there are true minterms in the 4 corner cells, they are also considered neighbors. So, I can make a big cube of size 4 using the 4 corner cells which is show like this. How? Let us write down and see. This cell corresponds to 0 0 0 0, this cell corresponds to 0 0 1 0, the left one corresponds to 1 0 0 0 and this one is 1 0 1 0. You see, last variable is always 0, second variable is always 0, the first and third are changing. So, same way first and third will cancel out and this will be equivalent to B bar D bar, right. So, the same concept you can make cubes as you wish. If you have this and this, you can make a cube like this, right. If you have this 4 and also this 4, then you can make a cube of size 8 like this. Same concept you can use, right. So, this is the same Karnaugh map where I am showing the cells labeled by the decimal equivalent of ABCD values. So, numbers are made like this 0, 1, 2, 3, 4, 5, 6, 7 and you skip to the last one 8, 9, 10, 11, then 12, 13, 14, 15. This is because this 1, 1 is coming first before 1, 0, right. Similarly, in the columns these are reversed because 1, 1 is coming first, then 1, 0. All right. Now, let us take some examples. Let us take a function like this, where you can see that there are 6 true minterms. Now, if I follow our rule, let us try to get the cubes construct. This can be one cube, I cannot make it any larger. This is one cube, these two ones they are adjacent, this is one cube. Now, one thing you see, this is also a cube, I am showing it dotted, this and this, you can also make a cube out of this, but this is not required because I have already covered all the true minterms with these 3 cubes. So, I do not require this cube anymore. Okay. This will be my best solution, minimum number of cubes which is covering all of them, but if I consider this dotted cube also, it will not make it any minimum, it will be even one more. But here what is the solution? These 2 cubes 0 1 which is A bar B and 0 0 0 1 D cancels out, C is 0 C bar. Then let us consider this one vertically. So, 0 1 and 1 1 A cancels out, B is 1, it is B and it is 1 0. So, C D bar, and the last one this top and bottom 0 0 and 1 0, A cancels out, B is 0, B bar and 1 1 C D. This is the minimized form of this function, right. Let us take another example. Let us take an example like this. Well, some of the largest cubes that you can immediately see is one is this, a cube of size 4. There is another cube of size 4 you can see, which will be these 2 plus these 2. You see, you can take these 2 separately, but this will not be the biggest one, because you can also take these 2, this will be the bigger one, and these 2 ones are still remaining. You can of course take a cube like this, but again this will be left out, but instead if you take a cube like this, then this will cover everything. I do not need any further cube. So, what will be the expression? This column, this A and B are cancelling out, AB will not be there 1 0. So, just C d bar plus these two 4 0 0 0 1 which is A bar and 0 0 and 1 0, C cancels out D bar, and lastly you have these two 0 1 1 1 means B and 0 1 C bar D. This is your minimized form. So, once you do it like this, you cannot minimize it any further. Just the thing that I mentioned, let me just tell it once more. Suppose we had constructed a cube like this, we had constructed this cube also like this, biggest possible, but suppose I also have constructed a cube like this, then this cube will also remain, this one will also remaining left out. So, I will also have to include it. So, you see I need one extra cube here, and this cube, these two, this is redundant because the cells that this cube is covering, these cells are already covered by some other cubes. Okay. So, a particular cell, a true minterm, need to be covered by at least one of the cubes. So, if I have one cube whose cells are already covered by some other cubes, I do not need to include that cube at all, I can leave it out. That is why I can remove this cube from my map and only 1, 2 and 3 this cubes will do. Okay. This is what we have done. Take another example. This is a very nice example, regular example, which shows 4 ones in the corners. This is very easy. The middle 4 will be one cube and the 4 corners will be these will be another cube. So, what will be the expression? The 4 middle one will be 0 1 1 1, it will be B, 0 1 1 1 again D, or the 4 corner ones 0 0 1 0 B bar, 0 0 1 0 D bar. This will be the function B D or B bar D bar, right. Let us look at some more examples. Take an example like this. So, here again let us try to make the cubes as large as possible, like one I can see these 4 I can make, these 4 I can make, these 4 I can make. Now, you see these two ones are being left out. So, I can make these two together, or I can make a cube of 4, these 2 plus these 2, right. This is the biggest. So, this will be my best cover. So, if you do it this way, this long one A, B are cancelled, it will be C bar D plus this cube on the left, it will be B and C bar, and these two 0 0 and 1 0, it will be B bar and 0 1 1 1 C cancels out D. This will be the minimized form, right. So, when you choose these cells, you should be judicious, you should not select something like this, I select this, I select this, then I select this. This is not minimum, because I can make it bigger, I can make these two and these two to make it a cube of size 4, right. So, I will try, means here I shall try to make it as large as possible, the cubes. Okay. This is another cyclic kind of a structure, like you see I can find these 4 cubes, but the other 4 ones are isolated. So, I can have one cube with these two, one cube with these two, one cube with these two, one cube with these two. So, what does this mean? See, let me again go back. So, our first premise or assumption was that we try to make the cube as large as possible. Okay. The second thing I mentioned, that if I find that a cube is covering some cells which are already covered by some other cubes, then I can drop or delete this cube, I do not need this. Okay. You see, in this example, the first thing I am saying is that this is the largest cube, okay. But the other 4, well, I cannot leave them out, because each of them is having at least one which is not covered by anyone. These are not covered by any other cube. So, when we include these 4, you see that the bigger cube is no longer required, because the 4 ones in the bigger cube, they are already covered by these 4 smaller cubes. So, even though this is the bigger one, I do not need this. So, my cover here will look like this, because this middle one will be redundant, is not required. So, what will be the expression? The left one will be A bar B and 0 0 0 1 C bar. This top one 0 0 0 1 will be A bar C D, plus these two will be 1 1 1 0 will be A and 0 1 is C bar D, plus these two 1 1 is A B and 1 1 1 0 is C. Okay. This will be my minimized form, but if you also include this middle one, then you will also include another term which is redundant, not required. It will be actually B and D, BD. BD is not required at all. So, you unnecessarily you are using 5 terms. These 4 are sufficient. These will be covering BD automatically, right. This is something you should remember. Okay. Here, let us take a slightly bigger and a more realistic example. Suppose we are trying to design a 2-bit adder. So, how is this 2-bit adder? It takes 2 numbers, these numbers are 2 bits each, and adds them up. Let us say one of the number is 0 1 and the other number is 1 1. So, if I add them up, 1 1 is 0 with a carry of 1, 1 0 1 is 0 with a carry of 1. So, the final carry out will be 1. So, my sum will be actually 3 bits, 2 bits and a possible carry out. So, the sum will be 3 bits. So, whenever you add 2 2-bit numbers, your sum will become 3 bits, 1 more, right, because there is a chance of 1 carry bit coming out, right. Let us look into this example and see how you can use the Karnaugh map for minimization. Well, here first let us look at the truth table. This is the truth table of the adder. So, just recall, in the adder I had said that there will be 4 inputs, the first number A1, A0, then B1 and B0, and there will be 3 outputs S2, S1 and S0. Let us see, in this truth table I am showing these 4 A1, A0, B1, B0 are the inputs, and there are 3 outputs S2, S1, S0. So, for 4 input there will be 2 to the power 4 or 16 min terms, which I am showing in 4 rows. So, 0 0 0 0 0 0 1 up to 1 1 1 1, there are 16. So, if you just add, you think in terms of equivalent decimal, it will be easier. 0 0 plus 0 0 means 0 plus 0 is 0. So, sum is 0 0 0. 0 plus 1, sum is 1, which is 0 0 1. 0 plus 2, 1 0 is 2, sum is 2, 2 is 0 1 0, 0 plus 3, sum is 3. So, 0 1 1 is 3, 0 1 is 1, 1 plus 0 is 1, 0 0 1, 1 plus 1 is 2, 0 1 0 is 2, 1 plus 2 is 3, 0 1 1, 1 plus 3 is 4, 1 0 0, 2 plus 0 is 2, 0 1 0, 2 plus 1 is 3, 2 plus 2 is 4, 1 0 0, 2 plus 3 is 5, 1 0 1, 3 plus 0 is 3, 3 plus 1 is 4, 3 plus 2 is 5 and 3 plus 3 is 6, 1 1 0. Now, in this Karnaugh map, we are showing the Karnaugh map corresponding to the output S 2, that means this column of the truth table. So, how many ones are there? 1, 2, 3, 4, 5 and 6. So, you see there are 6 ones corresponding to this. You see first one corresponds to 0 1 1 1. So, 0 1 1 1, this one. Second one is 1 0 1 0, 1 0 1 0, this one. Third one is 1 0 1 1, 1 0 1 1, this one. Fourth one is 1 1 0 1, 1 1 0 1, 1 1 1 0, 1 1 1 0 and finally 1 1 1 1, right. So, these are there. So, now if you try to form the cubes in this case, you see that you will be getting a large cube here, you will be getting a smaller cube here and another smaller cube here. That is all, you cannot minimize any further. So, what will be the expression for S 2? Your S 2 will be this bigger one, A 0 cancels out, only A 1 and 1 1 and 1 0 B 1, A 1 and B 1, or let us take this one first 1 1, which is A 1 A 0 and 0 1 1 1, that means B 0 B 0, or this one 0 1 1 1 is A 0 1 1 B 1 B 0. This is the function minimized form, this is the expression for S 2, right. Okay. Let us now see what will be S 1. Similar is the case for S 1. If you look at S 1, there are 1, 2, 3, 4, 5, 6, 7, 8 ones, and if you check, the 8 ones are distributed like this. So, you see here the cubes will be like this, you cannot minimize it too much, these two, then these two, then here these two, and these two are isolated ones, you cannot group them together, they will be isolated. So, there will be 1, 2, 3, 4, 5 and 6 cubes. So, the expression for S 1 will be slightly bigger. Look at this one, it will be A 1 A 0, A 1 A 0 and 1 1 1 0 will be B 1, sorry not A 1 A 0, A 1 dash A 0 dash, A 1 dash A 0 dash B 1, okay. Plus let us look at this one 0 0 and 0 1 A 1 dash, this will be A 1 dash 1 0 B 1 B 0 plus let us look at this one 1 1 1 0 is A 1 0 0 B 1 dash B 0 dash and this one 1 0 A1 A0 dash and 0 0 0 1 is B1 dash and the two isolated ones. This one will be 0 1 0 1, which means A1 dash A0 B1 dash B0, and the last one will be 1 1 1 1, which is A1 A0 B1 B0. So, you see this expression is a little more complex, but this is the minimum form. You cannot minimize it any further. Okay. All right. Now, finally, the expression for S0, the last one. Here you see for S0 there are 1, 2, 3, 4, 5, 6, 7, 8 ones, which are distributed like this. Now, these are pretty nicely distributed because you can very nicely form the cubes like this. One cube will be this, these 4 ones, another cube will be this, these 4 ones. So, S0 you can write, these two will be A0 and 0 0 and 1 0 B0 bar plus these two 0 0 and 1 0 A0 bar 0 1 1 1 B0. This is the minimum form, right. So, in this way you can minimize the expressions. This is the minimum form. So, we have seen that in case of this 2-bit adder, so how we can create or represent the 3 output functions S2, S1, S0 in the Karnaugh map, and then use the cubes to minimize the sum of products expression. So, we have seen means how to minimize these functions earlier for 3 variables and now for 4 variables. So, Karnaugh map is very easy to use, very simple graphically. If you once you can find the cubes from there, directly you can write down the minimized form. That is the big advantage. Okay. So, with this we come to the end of this lecture. In the next lecture, we shall be looking at a few other issues and concepts regarding the Karnaugh map method of minimization, before we move on to some other technique which is more systematic, which can be used for larger functions for minimizing switching expressions. Thank you.